All right, everybody. Woo, really close. All right, everybody. We are out. It is now officially 2:30, so I didn't want to jump the gun. But let me say thank you and welcome to the Slang Birds of a Feather. I am Shannon Woods. I am a technical program manager at NVIDIA and also the working group chair of the newly accepted Slang Working Group at Khronos. And I'm really excited to be here and share a bunch of cool stuff about slang at the BOF. So just giving you a preview of what we're going to cover here. I've got notes on, an overview of what slang is for anybody who's not familiar, community and feature updates. After that, we're going to have a presentation from Simon Potocnak, and followed by Andrea and Machizaud from Adobe. Both of them are going to be talking about their own experiences with slang and things that they've learned, stuff that might be useful to you as well as you work with slang. And then finally, at the end, we're going to have a section going over slang's mission and roadmap, where slang is going from here. And that'll be presented by Yong, one of the principal language architects of slang. And then we've got some time reserved at the end for Q&A. So what is slang? At its core, slang is both a shading language and a compiler that can take that shading language, ingest your code, and target multiple graphics APIs and compute platforms. So you write your shaders once in slang, and the compiler can generate HLSL if you're targeting DirectX. It can go straight to SPIR-V if you're going for Vulkan. It can generate metal shading language if you're targeting metal. It can do Wigzl, the WebGL shading language, or WebGPU, sorry, shading language if you're targeting WebGPU. And it can even target CPU side code via C or compute platforms like CUDA and Optic. But slang's cross-platform reach isn't its only strength. Slang brings modern programming features like generics and interfaces that you might be familiar with from languages on the CPU side like Swift and Rust into the shading language world. This enables developers to write reusable and specialized shader code in a robust and type-checked way. And it also offers first-class support for automatic differentiation. That allows for the generation of forward and backward derivative propagation code for arbitrary functions, which is a crucial capability for modern neural graphics. And at SIGGRAPH Asia, we announced that Slang, originally begun as a project at NVIDIA, had officially become part of Khronos. This move was critical because it allows for multi-company governance of the language while still doing all of our technical development completely in open source. This makes Slang a little bit different from most other Khronos working groups in that our technical output is a product of the open source community, not the working group. And you don't have to join Khronos to contribute, even at the level of core language decisions. The Slang developer community is very active. We've got more than 50 contributors active in the last 6 months, and over half of those have been from outside of NVIDIA. We've also now got over 4,300 GitHub stars, surpassing our peer languages. And our Discord has now grown to over 800 members. If you were with us at the Fast Forward on Monday, I said around 800. We passed 800 here at SIGGRAPH. It's really easy to get started. There's even a web playground where you can type your slang right into the browser, get IntelliSense-like features thanks to Slang's language server, and see the executed code right there in your browser window thanks to the WebGPU implementation. We're really proud of the community that's growing around Slang. And since our Khronos launch, we've welcomed 3 new committers from outside of NVIDIA who've already contributed significant new features and language proposals. Committers are the technical stakeholders of the Slang project, and they participate in technical decision-making and project steering. These new committers are members of the Slang community who have demonstrated commitment through consistent contribution track records, and we're really happy to have them on board. Our subreddit is getting active. Big shout out to Simon for his great work as a volunteer moderator there. You're actually going to see a presentation from him just after I'm done speaking. And it's awesome to see all the cool stuff that people are building with Slang. For example, a small team is developing an open source real-time planetary terrain generator plugin for Godot. And they've used the Slang Playground to put together a really cool demo. Sasha Willems, whose Vulkan tutorials you have probably used if you've learned Vulkan, has added Slang shaders to all of his Vulkan examples. And this is fantastic news for anyone looking to learn or use Slang in real-world Vulkan projects. Now, our goal is to make Slang as accessible and powerful as possible. And that starts with our developer education efforts. For those who prefer to learn at their own pace, our Slang developer blog features an in-depth series on neural graphics, a crucial topic for modern development. But for more interactive learning, we've been hosting a series of virtual community meetups. These are hands-on sessions that allow you to code along with us and ask questions in real time. Our past topics have ranged from compiling your first shader to a detailed look at the reflection API to tinkering around with Gaussian splats. So we've got a session upcoming in September, which you can get the registration info for by following this QR code. That will be looking at Slang's module system, and it's going to be hosted by Yong. And then finally, we've put a lot of work into making sure that Slang fits into your existing workflow. We've integrated with essential debugging tools like RenderDoc and NVIDIA Insight, but we're proud to announce that there is new support for crash debugging using Insight Aftermath to help you analyze your shader crashes. And then to help you improve your iteration loop work faster, the Visual Studio Code extension that we just launched now has a dedicated playground pane, giving you the same functionality as our web-based playground right there in your IDE, freeing you from having to deal with all of that window setup. Taking a look at our list of features, this is just the most interesting new features since the launch at SIGGRAPH Asia. You can see the team has been busy. So our efforts have focused on enhancing every aspect of Slang. We've made substantial improvements to the core language, added sophisticated features to the type system, and expanded support for advanced GPU features across various platforms. Each item on this list contributes to a more robust, powerful, and efficient shading language. One thing I want to call out in particular is we recently landed some serialization changes that allowed us to get up to 3 times the end-to-end compilation speed for small shaders going to SPIR-V. So we're continually working on features like this to help make Slang better and better for your daily use. So with all that said, I'm going to go ahead and bring up the presentation from Simon and let you hear from folks doing a deeper technical look at Slang.
Hello everyone, my name is Potocnak. I'm an university student, and over the past year I have been building my hobby renderer that supports classical rasterization rendering, but also path tracing using ray tracing hardware with Slang. And today I want to share my experience with the language that I had so far. So here are some images. This is rendered using ray tracing pipeline. This is rendered using rasterization pipeline. And finally, this is again rendered using ray tracing pipeline. There are many reasons why I have decided to switch from GLSL to Slang, and most influential ones were its out-of-the-box support for GPU ray tracing, modern syntax, modularization, and an official extension for VS Code. Transitioning from GLSL was quite straightforward. However, I mainly struggled on how to receive vertex attributes, how to communicate between 2 shaders, and how to pass data from GPU to CPU using uniform buffer objects or shader storage buffers. This was mainly because of the syntactical differences in those 2 languages. Slang allows you to write multiple shaders into a single .slang file, but in order to preserve readability, it is most important to determine when to split them into multiple files, and when it is okay to keep them in a single file. So when to split them, the decision was driven mainly by the complexity of the shaders, existing modules, reusability of those shaders, and how shaders depend and communicate with each other. So for example, ray tracing shaders were kept in a single file since all the ray tracing shaders are closely coupled together, and it was much easier to follow ray payload that way. On the other hand, main light path shaders were separated into vertex and fragment shader files, mainly because if I were to keep both shaders in a single file, the shader will be quite lengthy and hard to navigate. Simple effects like post-processing and depth prepass were kept in a single file. It is important to mention that most of the code is abstracted in the modules that I will talk about shortly, and modules are separate files which further help to reduce the bloat in the shaders. And lastly, I want to point out that when multiple shaders are written in a single file, .spirv files have to be produced for each and every one of those shaders. So if you have vertex and fragment shader in a single file, you have to produce .spirv file for each and every one of those. Modularization allows you to define and implement structs, functions, enums, etc. in separate files and include them either in other modules or in the shaders themselves. Every module can be separate .slang file, and they have to start with the module keyword followed by the name of the module. In order for compiler to know where to look for modules, you have to provide it with -i option, which stands for include, where you specify the directory where modules are located. Otherwise, the compiler will look in the root directory relative to the directory where shaders are being compiled. So my project is making use of the modules, and most important modules are core, light, surface, and material. When using modules, you can either import or include them. The difference is that modules located in the root directory relative to the path provided to the compiler can be accessed using import keyword, whereas modules in subdirectories must be accessed using #include, which specifies the subdirectory and the .slang file where the module resides. In this example, the math utils is in subfolder, and import will not know where to look for it. And for this reason, you have to use the #include and specify the subdirectory and the .slang file where the module is located. Alright, so now let's talk about specific modules and their usage. First off is the material module that is mostly inspired by model viewer example from the Slang repository. It is built around two interfaces, material and BRDF. The material interface is used to retrieve information about the shaded surface, while BRDF interface, on the other hand, holds the data needed for sampling and light evaluation. The material is responsible for preparing the BRDF, which means that BRDF implementations are never instantiated directly. Major advantage of this method is that this module can be used in both ray tracing and rasterization without having to change a single line of code. In this example, you can see both interfaces and notice how prepare function in the material interface returns concrete BRDF instance. In the second example is the simple implementation of the material interface that returns cooktorrent's GGX BRDF model, and material properties like roughness or color are set either during committed geometry hits while ray tracing or during fragment shading in rasterization. Setup like this made it easy to support different types of materials, including both specular and diffuse surfaces. And in the future, I'm also thinking about changing the interface to support full BSDFs so that it can handle both reflection as well as refraction. Since Slang support interfaces, I will probably follow a BXDF style design like the one used in the famous PBRT book. Next module I want to talk about is about lighting. Lights are created in a similar fashion to BRDFs. They are defined in a separate module that contains the light interface along with its implementations. The interface defines a single method called illuminate, which is responsible for calculating the light reflected off the surface. To perform this calculation, it requires an instance of BRDF implementation, surface information, and outgoing direction. Many different shaders require information about lights in the scene, and having this in a single module, I could just import the module and retrieve the necessary information. So for example, when doing ray traced shadows, I could just import the light module get the direction of the directional light, and shoot my rays in that direction. In addition to the standard implementations of light interface, such as point lights, direction lights, and area lights, I also created concatenation structs. These allow you to either create arrays of light or combine two light sources into one object. With this approach, I could merge all lights in the scene into a single object and simply call .illuminate on it to compute the final surface color. In this example, we can see the light interface and directional light implementation. As mentioned, to evaluate the light going into outgoing direction, it needs to have access to the specific BRDF instance and a surface, both of which are passed as function parameters. Thanks to the use of concatenation structs, passing light data to the GPU becomes quite straightforward. As you can see, the struct on the CPU side is identical to the one on the GPU side. A simple mem copy to a mapped pointer from a uniform buffer object will correctly populate the data, assuming of course all light types follow the STD140 memory layout. And lastly, this is how light environment variable looks like in practice. It contains all light sources in the scene, and to be fair, it's quite big of a type. Next, I want to briefly discuss pointers and buffer device addresses. In ray tracing, we don't have the usual vertex attributes passed per draw call, like in rasterization, and instead all the geometry data has to be made available to the shaders up front. What I do is that for every instance in the top-level acceleration structure, I create an object info structure. This structure holds addresses that point to correct locations in the vertex and index buffers that are referenced by the bottom-level acceleration structures. Once the top-level acceleration structure is hit, I can use the instance index function to access the correct object info that, as mentioned, holds geometry information about the intersected model. Then, using the primitive index, I look up the hit triangles indices from the index buffer and use those to fetch the correct vertex data by dereferencing the vertex pointer stored in the object info struct. In order for this to work, however, device addresses of the vertex and index buffer must be retrieved using Vulkan's buffer device address feature. In this example, you can see what was discussed in practice, and as you can probably tell, it is much simpler than it sounds. Here I use the instance ID to get the correct vertex and index data, which are then used to look up the correct vertex attributes via the primitive ID function. Those vertex attributes contain things like normal vectors, tangent vectors, or positions of those vertices. And lastly, I want to discuss ray queries. Ray queries allow you to use hardware ray tracing features without having to set up full-blown ray tracing pipeline. Slang makes it incredibly simple to work with ray queries, and in this example, you can see the intersects p function that returns boolean whether the given ray hit anything or not. Note that the ray description type provided as the first parameter to the function is defined by Slang and not by me. This utility function was located or is located in the utils module, and thus it can be used in any shader you want. In conclusion, Slang is a modern, intuitive, and fast-evolving shading language that's revolutionizing how shaders are being written. It's quickly gaining popularity, and for example, official Khronos Vulkan tutorial is now using Slang. Sasha Willem's Vulkan samples have been ported to it, and Slang compiler is also part of the Vulkan SDK by LunarG. The language is supported by a live and active community, where even the core developers of the language are available to answer the questions. While I couldn't cover all of its features here, Slang also comes with a lot of tools like Slang Reflections API, Slang Pi for Python, and the online Slang Playground, where you can test the Slang shaders in your browser. And lastly, if you have a cool project that is open source and is using Slang, please feel free to share it on this small website that I built. If you have any questions, contact me at this email address, and thank you for your attention.
That presentation was from Simon, who also moderates our subreddit and does a lot of work for Slang. So I was excited to see that. Up next, I'm going to call up, as soon as I can find my mouse pointer, I'm going to call up Andrea Machizaud from Adobe, who is going to share his own perspective.
Hi everyone. Yeah, much better. I'm Andrea Machizaud. Thanks, Shannon, for the introduction. I'm a software engineer at Adobe, and I'm going to present you the experience we had with Slang that we tried on Adobe 3D Substance Rendering Engine. Who are we? We are part of Adobe Substance division, and we are the team that implements a photorealistic rendering engine. We ship in various Substance applications. Our engine can run on CPU or GPU, multiple architecture, x86, 64, ARM, and we use Vulkan or Metal based on the platform as well. I won't repeat what was presented before. We also try to leverage the ray tracing API of each application, of each graphics API where we can. And here are some visual, if you know what it looks like when we ship an application, just to give an idea. So, art by Sinolai in Substance Designer, art by Pauline Boiteux and Louise Moulin in Substance Designer, that's just a shipped last month, I think. And an in-viewport view of, again, our engine into Substance Sampler with an art made by Yong. The problem statement, as I said it, so why Slang? The way we write our shader code base and we maintain it is becoming more trickier and trickier because we have an ever-growing feature set and complexity to manage. We adopt a style where we want to write once the shader source code, and we want to compile that everywhere. So we have this kind of unified way to write the shader source code, and if you're not using Slang and you try that, you have this kind of what we call GLSL plus macro soup, because you need to handle all those constraints of different use of languages. So yes, we use macro to try to abstract any language difference that you can encounter. We choose to have this kind of what we call an emulation layer, because across graphics API, they don't always have the concept that match, and we want to have that, so we have to maintain that into the engine. For example, if you use Vulkan with the ray tracing pipeline, and if you go to Metal or even C++, this is not a concept, right? So if you write that targeting this feature, you need to emulate something at some point. And another issue that is ever growing is that you have several compiler toolchain to maintain. If you have C++ shader, you have the usual C++ compiler. If you want to target GLSL like we do, you have GLSlang or shader C. And you go to Metal, you have the Metal compiler. So all those things are quite consistent, but still a little bit different to maintain. And because we put all those constraints to ourselves, our explorability is heavily limited because you can only do as much as the least capable source code language that you want to use. So we would like to do more, but we are quite constrained actually. Why was Slang appealing then? And why am I here today, I guess? I think Simon made a lot of points, and I was going to make a list, but I won't repeat everything, but in a nutshell, I think Slang mission statements, Slang open governance, Slang high-level capabilities, and the collaboration we had was actually great. And so that seems it checks a lot of the box for us. Like I think I'm going to talk about that afterward, but we started like around last end of the year, 2024, and that was really appealing. And I mentioned the complexity management on the previous slide, and I just wanted to highlight a couple of features of Slang that was really appealing to us, that we really want to leverage at some point. Shannon, I think you mentioned that, Simon too, interface and generic. It's a really, really useful tool that we take for granted in high-level language, that you can abstract things very easily and you can prototype very fast because you can just swap implementation, right? If you do that with GLSL, which is this kind of C API, it's much harder because you have all this source code explosion because you want to handle all those cases. So this is not as fast to iterate. Something maybe that was not mentioned, but which is really cool about that is that if you write your code targeting interfaces, you can make the choice of what is the implementation very late in the pipe, because you can write that in Slang, and it's only when you integrate that into your engine and you want to link that you can make a very late choice about what to choose. So again, it's another flexibility point. Another one, modules, without repeating again, because it seems to be the thing that people really love. It's so much better, especially if you come from a GLSL standpoint, is you can actually organize your code the same way you would organize your, I don't know, C++, any kind of code, right? If you try that with GLSL, you have one single translation unit on it to bring the whole code base, basically. On this, it just doesn't scale. A cool thing that goes with it, yes, you can use Slang to take GLSL and go to SPOV. You can also say, I want to take GLSL and go to Slang module, which means that you can go step by step. You can actually have several translational units, the same way we do with other language, and you can link everything afterwards. So again, more flexibility to manage a huge code base that you may have. Is this the right one? Yeah. Multiple entry points into the same file. Again, Simon mentioned it, but this example is from the documentation, actually. I find that really clear that if you come from GLSL because you have to include and so on, this is not clear what comes from where. If you've ever done Vulkan ray tracing pipeline, you have this payload, and it's so convenient to have everything defined in one file and that you are able to pull this off very easily across the stage. Again, less code duplication, I guess better compilation throughput. I haven't measured, but I guess it's obvious that it's easier to manage. Shadow bindings. I added more information than Simon, and maybe I want to dive into that. As Slang target to be data agnostic regarding the code generation target, I think you have your own language to define your shadow bindings, right? You have what you call shadow parameters, opaque type, which try to abstract what is a texture, what is a buffer, and so on, structure, not structure. And also, what is on the right is really interesting to us, because if you start from scratch, yes, Slang can have a consistent binding model that you can use in your engine, and it's fine, but we have existing shader code, engine is years old, and we don't want to mess everything. We want to actually use Slang to target all binding, which is actually used. And thanks to the attribute, this is an on-ramp way that you can use Slang to actually just change part of the engine, but not everything at all. Last feature I want to highlight, otherwise there is a long list for that. Capabilities. It's a lesser known feature, I feel, because I don't encounter that much. It's really, really useful because it means that you can have a function, a module, a struct, any of those things, you can annotate that with a requirement. And Slang will infer whether your actual final call is possible and compatible. And for example, if you use GLSL, it will automatically infer what is the right GLSL version to use, the extension to enable, and so on. So it's really, really convenient because today this is something we do manually. And I guess even if you target DirectX, HLSL, or so on, you have to maintain what is the right shadow model to use or the version to use. And as a bonus, you have the target switch. I don't know if you know that, but I wanted to illustrate also that even if Slang brings all this abstraction, you can always dive right in. I want to specialize this path because I know exactly what I want to do for this. So if you come from ISM, this is not at that point, but you target GLSL, you know exactly what you want to do. You can still do that using Slang. So it's kind of convenient to choose your level of abstraction on that. What I've utilized, so like I was saying before, the team gathered last year. We tried to have a focus of a couple of weeks on to try it for ourselves, because at that point, this is just me reading the documentation and so on. And we had one important goal in mind, which is we have this existing engine, this huge shader code base to maintain. Our focus is what is the best way we can migrate this shader code base to Slang, because this is the hard part here. Everything is appealing, but we cannot just use that. We need to find a path toward that. Without reading all the slides, there is this idea of on-ramp, which is you start from whatever you have today and you go towards Slang incrementally. So based on what I showed previously, one of the things that was of interest is to just change the shader toolchain replacements. Like we have all of those. What if we just use Slang for everything? There is a command line API, command line tool that you can use, or you have the compiler reflection API to do that. That was interesting. Modularization, we did something similar to Simon, that we have this semantic split of module that this is my camera module, this is my lighting module, this is light transport algorithm. So it's just so nice and convenient to be able to reason that. And also, if you have a team that is non-trivial size, you can actually split the work across people, whereas before it's kind of tricky to get that right. And we even get to the point that for very limited scope feature or experimental thing, we're able to actually start new shader right from the go in Slang. So that was nice. Especially nice when you have those compute shaders. There is not really, it doesn't affect a lot of the engine, so it's just convenient to start with that. rapid work, those weeks of experimentation, actually we got more questions than the beginning. And obviously, like, we didn't know the technology, so we wanted to know more about that. So we have more questions. We weren't sure things were not exactly working the way we expected, and so on. So we reached that point. But we had more confidence that, yes, it's really looked like something modern that can really help you to scale better than what we have from at the beginning, right? I'll go briefly to that, but first, what happened then? We went to the Slang team and we debriefed all our findings. And there are a lot of things happening there, but like we misunderstanding of features, or we didn't know where to go to the computation and so on. So what was nice is we just sit together and we establish a dedicated community channel so that we can actually try to consolidate all those findings and to report them to them. Big company makes time to have all the legal approval to be able to contribute and so on, but I think we got there at some point. We have regular sync meeting, and we have this process to how to report bugs, how do we triage things. You provided us what is the right space to get fixes and so on, so that was nice to have. Going back to the previous slide, so it's just a snapshot of, at the beginning, discussing over a couple of months. It's not even a year yet, I think, that we discussed about that. So things were quickly solved, and other things are still pending. We need to discuss, and sometimes it's just on us to formalize a bit better what we had, because if you just put a line, this is not enough, right? So you want to make a use case, you want to provide that so that they understand the issue and they can resolve it. Going to what's next for us now, and I think the key message is that we want to keep modernizing our rendering engine, because we still believe this is the way to go. If I'm being honest, maybe this is on us, that we are not fast enough to catch up with your development pace. So I think the following months will just be, let's try to allocate bigger chunk of time so that we can actually properly formalize the issue. And we have this established, so maybe we can directly contribute some of the issue which has without IP to the Slang project. And I think this is just a nice thing, because we bring those production use cases directly to the community, and actually people can use that as an example, or that you can see that people have similar issue, and you can help us and you direct us into the right path. Just wanted to highlight two things that I think are really important to us in the engine at that point, because of this wide platform support. Is we have this philosophy, like I said at the beginning, write once, compile everywhere, and we try to find the right way. Like any GLSL shader is easy, because we discussed about that, and that was even in your first slide, like what is ingested, but we also have C++ shader. Like, how do we bring that to Slang? Is it the right way? We also support Metal. On what do we do with that? Like, do we need to rewrite everything? Is there a way to ingest a little bit of that so that it's like a prelude, and then we can go somewhere else? Those are really of interest for us, and we want to dive into that. And yeah, I think after that, we feel that it's confident, it's working great. So we kind of confident that at some point, without ETA, maybe at some point we'll succeed to modernize all the rendering engine on its regular code base to Slang. Thanks for listening to me, and I will pass the mic to Yong.
All right, so next up, I will be talking a little bit about Slang's missions, some of the higher level design philosophies, and then I would like to share a little bit more on the future plans and roadmaps of the Slang project. So before anything, I would like to quickly talk about Slang's missions and goals. So we started the Slang project to help graphics developers to manage their large-scale GPU code bases more productively. And shaders used to be 5 lines of dot products like 20 years ago, but now there are hundreds of thousands of lines of path tracing code that people write today, and code bases at this scale will require a lot of software engineering practices for it to be maintainable and scalable. And here are some challenges that people often talk about when it comes to writing graphics code. For example, we need to maintain a clean software architecture to make the code readable and extensible. We need a code to be portable across different platforms, and that means they need to run like on Windows, Linux, Mac, or even on in the browser. And GPU code often need to be specialized for high performance execution, but that often means like really long compile times. So we need to provide a way to help manage that. And finally, to work with code at this scale productively, we need to provide really good tools to assist development like IntelliSense and debuggers. And an important fact to recognize is that a lot of these challenges are not unique to GPU code development. And there are a lot of lessons we can learn from the successful CPU languages. And Slang's approach to solve a lot of these challenges is that we're trying to bring proven programming language mechanisms to graphics app development and learn as much as we can from existing CPU languages. But that doesn't mean we're just going to copy and paste everything that's existing in the current languages as is to Slang. And instead, we need to think very carefully on how these features are going to interact with GPU architecture and how we can tweak those semantics to make it suitable for efficient GPU execution. And to be a little bit more concrete on that, let's say we're going to evolve this language to expose a new GPU feature that people are developing. What we don't want to do is to just look at our code base today and figure out the easiest path forward to hack the compiler just to produce a desired SPIR-V opcode. Or to figure out how we can add some arbitrary ad hoc attributes and modifiers here and there which would just end up forcing users to write ugly and really hard to understand code. So instead, we try to ask ourselves the question, like, what is the code that a developer would like to write when they want to use this GPU feature? And before adding any new ad hoc modifiers or attributes to the language, we always want to survey the well-known existing language mechanisms to see if there are anything that map well to this new feature that we want to expose. And here's an example of what I mean by that. SPIR-V added this physical storage buffer extension that allows your shader code to access any address in the memory space. And GLSL exposed this as the buffer reference, which is exposed via a new layout modifier and syntax. In Slang, we just make it a pointer because it's a well-known concept to all the developers. And this is the place where we don't want to innovate because it will make people's lives easier to understand pointer code. And another example, so a lot of developers are adopting this bindless resource idiom for flexibility in their code. And this is typically achieved by defining a large global array of resources and then turn every resource reference into an integer index into that array. We want to support this idiom to allow developers to write cleaner code. So we introduced this thing called descriptor handles that translates the integer indices into like the handles will be translated into integer indices by the compiler. And then when you write a code like using this descriptor handle, the compiler will lower this code to use either the native descriptor heap intrinsic on D3D12, or it lowers down to descriptor arrays on Vulkan, and you can even optionally use it use the compiler to generate code that's using the mutable descriptor extension. So for other targets where descriptors are already bindless, like in CUDA or Metal, a descriptor handle of T just maps to the resource type itself. Another example, so it's that Slang's exposure of this cooperative matrix extension. So we introduced tuples and lambda expressions to make it really convenient, like to define per element operations on a cooperative matrix. So here in this code, we are defining, so you see this map element function is taking a lambda function, lambda expression that that operates on each element of the matrix to compute that per element operation. So what I'm trying to convey with this example is that when it comes to designing the language, we want to start from the developer's perspective and focus on how to increase our users' productivity and how to make it a joy to code. And we would rather do more work inside the compiler to make every developer's life easier. And that's what we've been doing in the past couple of years. We added a lot of convenience features to the language, including modifier modules, visibility modifiers, optional and tuple types, variadic generics, lambda expressions, and so on. And if you haven't heard any of these language features, you can find more information about them in our user guide. So besides considering user experience, we also need to think about the future. Many problems today, they have multiple answers. And in this case, we need to choose the direction that will not only work well today, but also aligns well with where we envision future is ahead of us, like where the GPUs are evolving towards. And here's an example of what I mean. During the initial design of the Slang language, we wanted to provide a way for people to write structured code that can be specialized differently. So there are many existing solutions to this problem. C++ already have the preprocessor pound defines and templates. So we could just implement that. And if we do so, it will work well today on the GPUs today with all these calls eventually got inlined and inlined together and then translated to native GPU code and it can run. However, if we envisioned from the beginning of when we created this language back in 2017, that we envision that future GPUs will eventually support dynamic linking and true function pointers very efficiently. And in that word, we want our language to allow 100% separate compilation of modules. And that's when we decided maybe templates won't be the best fit for us going into the future, because templates essentially they will leak through the module boundaries. So instead, we support link time constants, generics, and modules that would enable separate compilation much more elegantly. This is also an advanced topic that I can spend an entire hour on, so I will leave it for another day. But the point here is that we are designing the language that works well today and scales well into the future. So I spoke a lot about the mission statement and design philosophy so far, and now let me switch gears to talk about some of the next steps of the Slang project. For the rest of the talk, I'm going to just color code a lot of the features that I'm going to mention to just give you an idea of what stage of that feature is in. And this will allow you to quickly tell if that feature is already available, work in progress, or something that will be made available in the short term or long term. I want to make it very clear that anything that's not marked as available today are just inspirational, and what I'm going to say is not a statement of commitment, but rather like to tell you what we are thinking right now. And there are many ideas we want to explore, and the actual priorities here will depend on community and user feedback. So first of all, I want to get through the point that the Slang project is not just a compiler for a specific language. It is a framework and ecosystem for dealing with shaders. And here's an overview of the Slang compiler stack. So we have an extensible set of front ends that can consume code in different flavors of syntax, like the canonical slang syntax, or HSL or GLSL-like syntax. And below that, your source code is translated into a unified or shared AST representation, and then that goes through the type system for checking, and then it lowers to Slang IR. And there are also many transformations, lowering legalization that's happened at the Slang IR level before it hits the backend. And then we have many different backends to generate your target code from that unified Slang IR. So outside the compiler, we also have the language server to provide IntelliSense support on all syntax flavors we support today, thanks to this shared AST structure. And with the trend of neurographics being developing, we think it's very important to make Slang as simple as possible to be called from Python. And we want to make it a great tool for developing neural models for graphics applications. So we introduced the SlangPy recently, which is a Python package that allows you to load and share, load a Slang modules, and then from Python, and then call into those functions directly from your Python code without having to write any boilerplates to create command buffers, setting descriptor sets, marshal your data buffer from natural layout to STD140 layout, and all that crap. So speaking of Python, a natural next thing we could do is you can easily extend this whole stack to support a Pythonic syntax. This will be something we will plan for the long term. It's not. It's hard to make this a short-term priority. But the point is that given this extensible framework, it's very easy to add new front ends without touching a lot of code. So with that, let's zoom out a little bit further and see the components around the core compiler. So another direction of the project is that we want to enrich our standard library to provide more than just a basic HSL and GLSL intrinsics. We are thinking about right now on adding a math.slang and neuro.slang as two standard modules that comes with Slang release. And the math.slang will cover many commonly used math types and functions, such as quaternions and geometry utilities. And neuro.slang is a module that implements the components for neural network training and inference. As we are talking about adding more standard modules, a next step is also to try to develop and provide a package manager to help bootstrap the community so everyone can start create and share their own Slang modules. Okay, now with that, I want to switch gears again and talk about the core language, the plans we have to actually evolve the language itself. So first of all, there are some simple convenience features that we added, but they're still missing in the language that would make these language features easier to use. For example, Slang has this optional T type, but we haven't added the chain member access from optional values yet. This is like the question mark dot operator that if you are familiar with like C#, they have this short form so that you don't have to test for non-values every time. And Slang also has tuple types, but we don't yet have structured binding to make the code more readable with tuples. And Slang has the enum types, but right now they are just simple integers. Languages like Swift, they support enums with payloads that will make it easy to define tag unions or sum types. And this will be a nice addition to Slang as well. Another thing that Slang should support is that we should support pointers with different address spaces. Right now, pointers in Slang are assumed to point to your device or global memory, and this needs to be extended to allow pointers to share memory as well. And to make pointers with address spaces easier to use, the compiler should also automatically infer the address space of a pointer when you pass it into a function. And we should also, so for example, if you write a function, we want to make it implicitly generic on the address spaces, so that if you are calling this function test from the caller with the values that are actually from different address spaces, the compiler should be able to automatically specialize your test function to different address spaces without you having to write explicit generics everywhere. And Slang supports generics with variadic type parameters, and that's how we use it to define our tuple types and ifunc types in the core library. However, we don't have variadic value parameters with people starting to write libraries for tensors and neural networks. Variadic value parameters can actually become more useful. And speaking of generic value parameters, we should also extend the type system to support constraint on generic values, so that I can define a function that works on a range of values. And this can be particularly useful as we are thinking about extending or relaxing the restriction of the built-in vectors and matrices to accept arbitrary sizes instead of just limited to be under 4. And when we do that, we will need to be able to define generic functions that work on vectors and matrices that work with a specific range of sizes instead of specialized to a specific size. And another area we're getting a lot of questions on is, does Slang support metal ray tracing? The current status is that Slang supports full HSL-style ray tracing API, and we can cross-compile it to either HSL or SPIR-V. But translating this API efficiently to metal is not something possible or easy to do. So one solution that we've been thinking about is we should introduce a new set of intrinsic functions that describe ray tracing in a slightly different way that can be mapped efficiently to all these targets. But that will require some careful API design to ensure that it actually does what we want it to do. And finally, although Slang is a shading language today, there is no reason to stop being at just a shading language. There have been a lot of experiments going on involving Slang for CPU programming as well. And one major step so the big gap right now in this language for CPU programming is error handling. Another one is lifetime management. So for error handling, we recently added the experimental support for the throw and catch keywords. So while these look like exceptions, they are actually lowered exactly as error codes. So it's very lightweight and very low overhead. And this is another example of Slang being designed as a GPU-first language. The alternative here to adding error handling support is to introduce exceptions to the language, which would obviously be a poor idea when you want to target GPUs. So we decided that Slang won't have exceptions. And even when we want to extend this language to have some CPU programming capability. And the big upside of this design is that the error handling becomes a general language concept that isn't tied to CPU execution at all. Because you can use this, you can actually use this feature today in your GPU shaders without any limitations, because in the end, they all lower to just ordinary control flow and error code returning functions. And for lifetime management, we introduced a defer keyword recently to help manage the destruction of resources. While this is not as powerful as C++ RAI mechanism, this is a very lightweight and works well for many cases. So similarly, the first statement is mostly used to manage lifetime on the CPU, but the language itself, this feature itself isn't tied to CPU execution at all, and it works just fine on the GPU. And finally, we're considering like adding a LLVM backend for Slang to support generating native CPU code and supporting like JIT compiling and execution, and also provide a native debugging experience with LLDB and GDB. The reason we want to invest more on CPU programming is that we eventually want to evolve Slang into a heterogeneous programming language where the host side logic can call into the device side functions seamlessly without any boilerplates. And the long-term vision for Slang is that it will become this modern language for writing GPU applications end-to-end with consistent syntax, first-class intelligence, and native debugging experience that works well for both your CPU side code and GPU side code. And with a powerful language, core language, and a convenient package manager, we have the opportunity to build a rich ecosystem for sharing cross-platform and heterogeneous software packages that's built with Slang. So yeah, that's everything I want to share today. If any of these directions excites you and you want to see them happen sooner, please join us to make Slang better together. You can scan this QR code to join our Discord server for questions and more discussions. Thank you.
All right, I think we only have a couple moments for Q&A, so I won't hold you up. I just want to throw this slide up here with your last two opportunities to get more Slang at SIGGRAPH. We have a course tomorrow on neural shading, as well as a class on Vulkan ray tracing, both of which will be taught extensively with Slang, and you can catch up on the lab that we had on Sunday. So with that, we'll take as many questions as we have time for.
Okay, I will try the first one. I'm interested in the open source part. My understanding is Slang open source the front end. I was curious about the autodev part. Is the autodev part open source as well, or?
Yes, it is. The entire compiler stack is in open source, so you can take a look at how it works.
I see. So the autodiff part is open source, and the processing on the IR, the LLVM IR, or Slang IR.
Slang IR. We don't include LLVM. Slang does not include LLVM. It's an optional. If you want to, we'll output C++ or C rather, and you can then pipe that into LLVM. But
so in that case, it does not need the CUDA backend to support this. It can directly go to the Spirit.
You can automatic differentiation is usable across all of Slang's backends.
Okay, thank you. Thanks.
Hi, so my question is regarding the modern function syntax that Slang seems to support, where you can use like the func keyword, and then you can do like variable name : type. Is there plans to support that going forward, or is that planned to be deprecated? Because I noticed that it doesn't get used on any of the slides here.
Yes, there's no intent to deprecate any of the modern syntax, so we provide that as another syntax flavor for people who are used from those modern languages, so they can feel comfortable writing Slang.
Okay.
Yeah.
Okay.
So both are supported. Like we designed this architecture so that it's very easy to extend to more syntax flavors. So we are not going to cut that down, or like we want to explore like extended language to make more people feel comfortable instead of restricting to a certain syntax.
Right.
Because the key value is not a syntax, it's the value we provide through the entire stack.
Right. Okay, that's helpful. I guess from my standpoint, what was kind of hard moving to Slang is trying to understand what is like the idiomatic way to write code, but maybe the argument there is it's sort of like
Yeah, that's a coding style decision that we will leave to each individual user.
Right, cool. And then the other question I had is, are there any plans to add sort of like project like TOML files or something that might help you to like tell the language server what features you want it to sort of like check for? When you're using stuff like, if you're targeting like WebGPU, for instance, like you need to use like the atomic keyword. It would be nice if there was like a way to say like, hey, this is like the version of Slang that I'm using to like communicate that to the language server so that you get those errors at compile time.
Yeah, actually, we just added a pound language directive that you can put in the first line of the source. You can do pound len like 2026 or something, and then that will tell the compiler and the intelligence engine what level, what language version you're writing against.
Okay, awesome. Thank you.
Hey, I noticed in the you had a slide talking about the Slang ray tracing API, lowering that to Metal, DirectX, and Vulkan. Have you given any thought to including a CPU ray tracing API as one of the targets for that as well? Because there are several applications where it'd be very useful to have a CPU ray tracing backend as well.
So what's your question again?
Are you going to support lowering from the Slang ray tracing API to a CPU ray tracing?
Right. So right now our CPU support is restricted to just compute shaders only, but extend that to like translate ray tracing calls into some CPU software implementation is definitely possible. But right now we haven't been prioritizing that work yet. Okay. But it's definitely within the capability. Yeah.
Yeah, so the Machine Learning Council is going to be up next. So if you have more Slang questions, we're going to hang around, just outside the back doors. So you can come up and ask all your questions there. Thank you.